Hi, I'm Tahmid Latif from NC State University in Raleigh, North Carolina, USA. I work with the Department of Electrical and Computer Engineering and the National Science Foundation Nanosystems Engineering Research Center for Advanced Self-Powered Systems of Integrated Sensors and Technologies, or ASSIST Center in short. Here at ASSIST, we are working towards developing ultra-low power, multimodal wearable sensors for health and environment monitoring. In this presentation, I'm going to talk about our preliminary investigation on low-level ozone on human biological responses. I will discuss our results and the correlation between ozone exposure, heart rate variability, and lung function. First, I'm going to talk about ozone and its relevance to asthma, followed by our ozone study protocol and our data analysis methodology. Then I will present our results on data correlation. Ozone is a common trigger for asthma exacerbation, and it promotes lung inflammation. It's not the only one, but studies suggest that ozone exposure at levels even below the US National Ambient Air Quality Standards, or NAAQS, of 0.07 parts per million or ppm can decrease lung function and increase respiratory symptoms in susceptible populations, individuals with asthma. With millions of people suffering, related healthcare costs are tremendous. For these reasons, an improved and cost-effective approach to asthma care and management would be beneficial from many ends. For this purpose, at ASSIST, we are working towards developing multimodal wearable engineered systems for vigilant monitoring of physiological and environmental conditions of an individual with the goal of improving health outcomes. These low-powered systems in the form of a wrist-worn watch and a chest-worn patch would perform correlated sensing of the user's health and ambient environmental parameters in real time. Data would be used to identify changes in the user's physiologic conditions and predict asthma exacerbations through advanced data analytics. The user can take actionable decisions based on customized device notifications. For example, they can perhaps take medication, suspend activity they're currently doing, or get indoors to possibly prevent an asthma onset. Our wrist-worn system here is equipped with a low-power ozone sensor that we developed. It also has temperature and humidity sensors. The watch uses data from the built-in environmental sensors as opposed to taking data from weather stations so as to utilize the environmental data with higher spatial and temporal resolutions. The eventual goal of such wearable systems would be to improve quality of life as well as impact the economy in the healthcare industry. Before testing and validation of devices comes understanding of this data. And for this work, we carried out a preclinical ozone study to investigate effect of low-dose ozone and the correlation between ozone exposure, heart rate variability, and lung function in a healthy control group. This study was a randomized double-blinded crossover study where test subjects, mostly sedentary, received exposure to ozone or filtered air in 2 separate sessions lasting 6.6 hours each. Ozone levels varied between 0.06 and 0.08 ppm at 24 degrees Celsius and 40% relative humidity inside an environmental control chamber at the US Environmental Protection Agency's Human Studies Facility in Chapel Hill, North Carolina. The ozone level in the study went up from 0.06 to 0.08 and then back to 0.06 in 1 hour. In this way, the ozone level varied between 0.06 and 0.08 ppm for the whole duration of the exposure. This corresponded to an average of 0.07 ppm, which is the US NAAQS standard for ground level ozone on a hot summer day. The protocol involved taking spirometry data and neutrophil count at baseline and then after each exposure. ECG data was continuously collected throughout the exposure with an off-the-shelf ECG sensor. In this work, preliminary data analysis was performed on data from 4 of our control group of test subjects. The ECG data analysis methodology involved utilizing signal quality index for reliable ECG feature extraction, then wavelet-based signal processing, followed by computing heart rate variability data. Signal quality index, or SQI, was computed using a 20-second window with a 5-second overlap and a 0.1 second buffer. If you look at the representative figure as an example, we can see that each dot illustrates the locations where a QRS complex is detected, and its color indicating the signal quality, ranging from green for high SQI to red for low SQI. For example, this raw signal has a false detection, has low SQI, while the clean signal has high SQI. Upper and lower threshold for our interval corresponded to a heart rate of 40 BPM and 180 BPM. We removed low signal quality data using a signal quality threshold experimentally set at tau equal to 0.95. This threshold was used for both the raw and the clean signal. But for getting the clean signal, however, we use the wavelet-based approach to get a better SQI. Here for cleaning data with SQI below tau equal to 0.95, we used a lower SQI threshold, which was empirically set at rho equal to 0.3. So essentially, we cleaned data with signal quality between 0.3 and 0.95. Data below 0.3 were of poor quality and hence was discarded. This process reduced the fraction of data removed. So for raw signal, on average, 44% data was removed, while for clean signal, the data removed was 33% using the wavelet-based approach. So this meant an overall reduction of 26% of the data removed. Hence, wavelet-based processing increased the quality of data retained for further analysis or processing. HRV statistics were computed over 5-minute wide windows in our case. And in here, we see a plot of mean heart rate versus elapsed time, this representative data, where heart rate in blue is for an ozone exposure and red during an exposure to clean filtered air. The raw signal was processed with Pan-Tompkins algorithm, and this resulted in some of the data to be removed automatically, owing to those segments corresponding to very low or very high heart rate. The figures on the right show how much data was actually removed after SQI filtering. Compared to the clean signal here, the raw signal shows more missing data segments. Hence, less overlap here, which shows less is the fraction of data retained. For the raw signal after SQI filtering, 25% data was removed from sessions with ozone exposure, and 28% data was removed from session with air exposure. In contrast, for signal clean with wavelet approach, 13% of the data was removed for ozone and 11% for air. Notice how some of the missing segments in the filtered raw signal actually appear in the clean signal, and hence we also see relatively more overlap here in the figure for clean signal. Here we see the mean heart rate data and PNNF50 for our test subjects. And this helps us realize the effect of ozone on the test subjects. Data was computed from the clean signal after SQI removal and wavelet-based processing of the signal. We noticed an increment in mean heart rate, seen here in blue, in 3 out of the test 4 subjects when exposed to ozone, subjects 1, 2, and 4. We also noticed how PNNA50 decreased for those 3 subjects when exposed to ozone. For lung function, we saw some decrement in FVC, in lung function, while there was elevated airway inflammation due to ozone exposure. Now moving on towards data correlation by combining heart rate with lung function data and neutrophil count. We did seem to observe changes in mean heart rate to have a positive correlation with changes in FVC and a negative correlation with neutrophil count. And these type of data would actually help us predict decrease in lung activity based on vigilant physiologic data monitoring and relevant data analytics. Obviously, a larger study is needed to properly justify these relationships. To summarize, we have achieved a baseline understanding of healthy subjects to ozone. To achieve a better estimation, data analysis with a larger sample size with data from the rest of the test subjects is currently in progress. In addition, we are running a follow-up study with mild asthmatics with our own custom engineered systems from ASSIST. Lastly, I would like to acknowledge the National Science Foundation for supporting our research, EPA for their Human Studies Facility, SAS Institute for collaborating on the data analytics efforts, and Martha Almond and Sally Ivins from UNC for help with the study. Thank you, everyone.